Hello everybody, we're going to go through a graphing exercise today. Our graph is the function y equals 2 minus x times e to the 3x. And in the following function, we're asked to find the domain, determine if there's any symmetry, even, odd, or neither, find the location of any intercepts, and the intervals where the curve is increasing or decreasing, and the value of any extrema, and intervals of concavity, as well as any inflection points, and then sketch this curve. So let's run through the entire graphing system here that we have. First of all, for the domain, we'll note that the function y equals 2 minus x is defined for all real numbers, and the function y equals e to the 3x is defined for all real numbers. So right away, we can state that our domain will be all real numbers. As far as the symmetry is concerned, when we talk about even or odd symmetry, a function will be even if we substitute negative x into the function and find that it would be exactly the same as the original function f of x. But a quick inspection of this function shows that substituting in negative x would certainly change the first term from 2 minus x to 2 plus x. So we can say right away it's not an even function. It will not be symmetric about the y-axis. As far as it being odd, it would be odd if substituting in negative x results in the negative, or the opposite of the original function. And again, substituting in a negative x for x in each part of this function would reveal that it is not the negative of the original function, so it's not odd. So this function will have neither even nor odd kind of symmetry. So we can take care of that right now. This is a function with neither even nor odd symmetry. So next we want to find the location of any intercepts. Well, as far as intercepts are concerned, x-intercepts occur wherever y is equal to 0. So if we set this expression equal to 0, we'll note that it would certainly be 0 at x equals 2, but that e to the 3x is never equal to 0. It's always greater than 0. So we only will have one x-intercept, and that is at the point 0, 2. I'm going to go ahead and I'm going to mark that on my graph right now. 2, 0, pardon me. The y-intercept would be found by substituting in 0 for x. If we do that here, y is going to be equal to 2 times e to the 0, which is to say at 2. So this graph will also pass through the point 0, 2. All right, so already we've got some information about this function. The next idea is that we have to be able to find where the function is going to be increasing or decreasing in order to determine maximum, minimum, and other extrema. So we'll go through and find the derivative, and I'd ask you to go ahead and pause and take the derivative yourself just to check this out, and then I'll put up my answer. Okay, if you found that y prime was equal to 5 minus 3x times e to the 3x, congratulations, you did that correctly. And we want to first of all find any critical numbers on this function's derivative, and we will find that our first and actually only critical number as far as the first derivative is concerned is at x equals 5/3. So we look to determine whether or not this function is going to be increasing or decreasing on either side of that function. So at 5/3, we'll note that if we substitute in a value to the left of 5/3, for example 0, that's going to give us a positive value. Whereas if we go to the right of 5/3 and choose a larger number such as 2, we note that this function is going to be negative. So this function has a maximum at 5/3 by the first derivative test, where it changes from increasing to decreasing. And we would want to substitute in, that's a DECR there we go. We would want to substitute in x equals 5/3 into the original function to find the y value right here. Doing so reveals the y value, y equals negative 1/3. Positive 1/3, pardon me, there's a sign error on my thing. 1/3 times e to the 5th. That's approximately, if you're looking at a calculator, that's approximately 49.5. So our maximum will occur at 5/3. And the number 1/3 e to the 5th. Okay, so 5/3 is 1/3 more than 1 and just slightly less than 50. Right about here is going to be our maximum. What else can we tell? Well, we need a second derivative. So again, take a moment, do your derivative, and we'll check out your answer and compare it to mine in just a minute. Okay, if you did your second derivative correctly, it probably came out something similar to this: 3 times 4 minus 3x times e to the 3x. Looking for any critical numbers from the standpoint of the second derivative gives us x equals 4/3. X equals 4/3. So we're going to go ahead and plot that on our number line. 4/3 is 1 1/3, right? So 4/3 right here. We substitute that into our second derivative, any numbers to the left and right, to find out if we have a function that is positive or negative. Substituting in 1, which is to the left, is going to give us a positive value. Substituting in any number to the right gives us a negative. So that means that we're going to have a shape that is concave up when it is to the left, and it's going to be concave down when it is to the right of 4/3. Now, if we want to, what we need to do is we need to find where that point of inflection is. So we again substitute in x equals 4/3 into our original function to find the y value that goes with it. In this case, we would find the y value to be at 2/3 of e to the 4th. And we would note that at 2/3 e to the 4th, that is approximately 36.4. So we're going to have an inflection point at the coordinate 4/3, 2/3 e to the 4th. And looking that up, 4/3 is right about here at 36, so slightly higher than 35. A little bit higher this time right here. And of course, our coordinate point right here for our maximum is at 5/3. Let me just move that over a little bit right here so we're in the right place, more or less. Okay, so how is this going to work out? Well, we have our intervals of increasing and decreasing. I'm going to use a different color to map those out right here. I'll notice that the function is going to be increasing on this entire interval from 0 to 4/3, and then decreasing on the interval from 5/3 to infinity. We'll also note that this function is going to be concave up all the way up to our value at x equals 4/3. So we're going to have a concave up shape. And then from 4/3 onward, it's going to be concave down. So we think, well, what should that look like? Okay, we're going to have a very small interval here where we're increasing in concave down, but increasing in concave up. So our graph, we might note right here that as x tends to negative infinity, we could take the limit of this function and find that y is going to tend towards 0. How do I know? let me go down here. Let's take a quick look at the function. If I were to take my limit as x tends towards negative infinity of 2 minus x times e to the 3x, we've got a product of two functions right here. The first part of this function, 2 minus x, is going to go towards infinity as x tends to infinity, to negative infinity. 2 minus negative infinity is 2 plus infinity, that's infinity. On the other hand, e to the 3x is going to go towards 0 because e raised to a negative large power is going to be a number that's very close to 0. Overall, the effect is that it's going to approach 0. So this is now my limit. And so we can say that with that information, this graph is going to come along the x-axis up to this point 0, 2. Then it's going to proceed going concave upward until we reach that inflection point. Then it'll increase and go in a concave downward direction. Finally, after the maximum, it'll start decreasing, going concave downward, and it's going to come right down and pass through this point at 2, 0. So it's a reasonable approximation of what this graph should look like right here with our point of inflection, our maximum, and our x and y intercepts along with the horizontal asymptote to the left at y equals 0.